Hello and welcome to Focused Hour Calculus. Today we'll be discussing the very basis of calculus itself, limit notation. Now, first, before we even begin, we have to understand how crucial limit notation is. Unlike a lot of the other stuff you'll learn in calculus, limit notation makes up the very basis of the almost everything you learn in calculus, whether that be derivatives, tangent lines, integrals, and so much other areas. Limit notation is very important, so having that core knowledge as the first step of learning calculus, or even reviewing calculus in general, is extremely crucial. So now that we understand, let's take a look at exactly what limit notation is. And in order to do that, we first have to understand how to express it. So, limit notation is expressed as three letters, lim, and then under those three letters, you're going to put a variable. We're going to assume the variable is x, approaching a value. So I'm going to do the value as a, and a is just any number that exists on a function. And a function can be explained on f of x. So here, let's assume the limit notation is regarding the function f of x. In this case, we put f of x right here, and equal sign, and the number, or the answer, goes here. So this may look extremely confusing, so let's take a look at an example. In order to do any limit notation, we should have a graph, or some way of expressing the function. It doesn't have to be a graph, but in this case, in the easiest way possible, let's do a graph. In this graph, there's an x and a y, and this graph is a straight line. Graph of f of x. In this case, there's a lot of points, an infinite amount of points on this function. Let's assume that the point we're talking about right now is a. A is right here. And here's the question. At the point which there is a, what is the limit notation of x approaching the value a of f of x? Now, how do we solve this problem? When you are given a point as the variable to which x is approaching, the only thing you need to do is look at the y value. So here, you look at exactly where this value of a reaches y. And here, assuming that every single one of these squares is 1, this is going to be 1. So the answer here is 1. And that's all you need to do. So for any singular problem where the limit approaches a variable that is a number, and it is known on the graph or on the function that is given, the very easy way to do it is simply to graph it and then find the value that y equals at the point A. Okay, well, this is very simple. Let's take a look at another instance then. So in this case, we don't have a graph. Instead, we are shown the function. So limit of x approaches, let's assume 2, at the function x plus 2. What is the answer here? Well, we know that right now that the line or the function that we are given is x plus 2. And we understand that y equals x plus 2 is a line. However, we don't really have to visualize this line even. All we have to do is find where exactly this line has the y variable, or what the y variable for this function at x equals 2 is. So we know that x is approaching 2, so where is the y value, or where does the y value approach as x goes to 2? In this case, you just have to plug it in. That's all you have to do. Don't overcomplicate it, just plug it in. And here, if we plug it in, 2 plus 2 would be equal to 4. That's it. The answer is 4. That's all you have to do for all these questions. So let's do one that's a little more complicated, but not too much, just to get the hang of it. Limit as x approaches 6 of x squared plus 2 over x. Oops, over x. What would that be equal to? You can pause and solve, or we can do it together. In this case, we just have to plug it in. So 6 squared plus 2 over 6. That would be equal to 36 plus 2 over 6. And that's equal to 38 over 6. Or we can simplify it so that we understand it is 19 over 3. And that's your answer. Okay, so we understand the first step in step 1 of limit notation. Let's do a step that is a little more complicated then. And here I'm going to introduce you to something called an asymptote. An asymptote. So what is an asymptote? Well, let's return to our good old friend, a graph, and start there. So an asymptote, in its very simple definition, is a location where there is no value that exists on a point x. So for example, assuming that we have a graph and point A has an asymptote, point A, that means right here, I'm going to draw a dashed line. And over this dashed line, any value of y cannot exist. And therefore, you'll see numbers approaching that value, but never reaching that value. Let me change to a line. For example, here, this is a possible value or a possible graph with an asymptote at x equals a. And there, no singular value on a exists. So then I ask you the question, what is the limit as x approaches a of this function f of x equal to? You can take a while to think about it, but this will be kind of challenging. The answer is that the limit does not exist. Let's think about why. So first, a limit is defined as where the function values or the y values approach as x approaches a. So here, let's take a look at the values one by one. So first, on the right side, as x approaches a, y continues to go up until it reaches infinity. This will continue to go up and it won't stop. So therefore, because it never actually reaches a, nor does it need to reach a, but we'll get into that later, the y value continues to go to infinity. But let's look at the left side then. On the left side, you see that the x value, or the y value, continues to decrease. It never reaches a, but it, once again, doesn't have to. We're looking at what value y approaches, not what value y is. So in this case, it reaches negative infinity. But neither of them are the same, because we understand that negative infinity is not equal to positive infinity. Therefore, because the values on either end are different, there is no limit. So once again, it doesn't have to be an asymptote, and this value a doesn't have to exist. The only thing you know is whether or not y exists, or the value approaching y exists and is equal on both sides. So let me make this more simple. For example, let's assume another graph, and here there is no asymptote, but instead there is a hole. So we have the line, and this is the graph. When x is equal to a, right here, the value doesn't exist. There is no value for when x is equal to a. In this case, what is the limit notation as x approaches a in the graph f of x? Think about it. Well, the answer is 1. Well, assuming that each box is 1, it would be equal to 1. Why? Why is it not does not exist? Why is it not DNE? The reasoning is, once again, because it's the value that y is approaching. It's not the value that it specifically has to equal to, it's the value that it is approaching. Therefore, you don't have to see it being anything or even existing, it just has to approach. So, for example, a graph instead that would be, let me draw it again, a graph that would be here that is like this, as the line approaches here. This does not exist, and when it approaches here, it does. And you're asked, what is the limit as x approaches a in this graph, g of x? Then it would be does not exist. Why? Because there is, while a value of a that has a given y, it does not exist because it approaches different variables. But as you realize, and as we've interpreted before, there is a right variable and a left variable to which y can approach. So how do we express a singular side? If I only want to know what is the value of y that x approaching a on the right shows, how would I be able to tell? Well, there's a way to tell by simply using another notation. So it's the exact same as x approaches a of function f of x is equal to question mark. But if I want to know what is on the left side, then I only have to do a negative mark. That means what is x on the negative side? So for example, this is the function of f of x, and this is a. In that case scenario, if I want to find what value does x approach on the left side, then I only have to do the negative sign. On the other hand, if I want to find out what is on the right side, so how does the right side approach, then I do the exact same thing, and can you guess it? It is a plus sign. Everything else remains the same. In order for a limit to exist, these two values have to be equal to each other. So, ignoring these two values have to be equal. If they are not equal, then the function does not exist. Okay, now that we got that under control, let's take a look at another circumstance entirely. What if we're not considering x to a as a number, but instead, what does it mean if we say limit of x to a, but a is infinity? So x approaching infinity, what does that mean? Let's draw another graph. In this case, where there is a line, oops, wrong axes. Okay, this is the line of f of x. So where does y go as x approaches infinity? Think about this logically. It's nothing too complicated. Y would also approach infinity, because that makes a lot of sense. As you go infinitely amount that way, the function f of x infinitely increases. So you have your answer. What about the other way? What if this is a negative infinity, as x approaches negative infinity? In that case, it's the exact same thing. The only difference here is that you're going towards negative infinity, because x is consistently and forever going to the left, where it is consistently decreasing. You're going to consistently decrease as a function f of x, therefore going to negative infinity. All right, infinity's done. Let's take a look at another way to solve the problem, specifically when there is an asymptote. So we've discussed asymptotes. Let's take a look at a horizontal asymptote. So the last asymptote we see intersected with the x-axis, which made it, once again, as you can see, a specifically vertical line. What if an asymptote was a horizontal line? So like this. And the function looked something like this. And here I ask you the same limit question. As x goes to infinity of f of x, what is the answer? This is 1. Well, the answer is 1. Because, think about this once again, as you continuously go towards the value of x equals infinity or infinity, this number doesn't cross the number 1, however, continuously approaches 1. And therefore, it's going towards 1 but never equal to, but that doesn't matter. It doesn't matter whether it touches 1 or not. It matters the fact that it's approaching 1, which the asymptote represents. Which is exactly why this will be equal to 1. Then what about negative infinity? What if lim x to negative infinity f of x? What would that be equal to? Well, that would once again be equal to 1. You're still going towards 1, just that this time you're going in the negative infinity direction in the x-axis. So in this case, it would still be equal to 1. Okay, so if you followed along right here, you'll notice a pretty interesting pattern. And that when you're being asked questions regarding when the limit of something is equal to infinity, there are certain rules that are very much useful that you can use. However, they'll be discussed in our second video of limit notation part 2. Make sure to follow along because we'll be discussing a lot of useful tactics which you aren't seeing right here. Useful tactics. Make sure to tune in to the next video where we discuss part 2 of limit notation, the first step in calculus.